Hi, this is Garrett Edmondson, and welcome to another in my series of videos about constructing a data warehouse. This video is going to be all about ETL, and specifically designing an ETL process for a data warehouse workload. This builds on the concepts covered in previous videos that I have produced, and so I highly recommend that you watch those in the order that I specified, as I will be covering many of the same topics and using that same vocabulary in a very precise manner to explain how to construct a data warehouse ETL process. My contact information is displayed there in the first slide, my email address, my blog, and my YouTube channel, where you can view all this information. So to begin with, an ETL at its most fundamental level is moving data from point A to point B. However, in virtually all data warehouse scenarios, this data that you are moving is located in a different place on your network, or even in a different network altogether. So one of the most important things to keep in mind for when you're thinking about an ETL process for a data warehouse is that this is your ETL extracting from the source is going to be the slowest part of the overall data warehouse solution. Well, why is that? Well, it's very simple. The ETL represents the slowest movement of data in the entire process. Think of your data warehouse server. Think of what I explained in detail in terms of throughput, megabytes or gigabytes per second, that you're able to deliver from disk to your CPU. Again, that's talking in terms of gigabytes per second. So imagine 2, 4, 6, 8, even 10 gigabytes per second of throughput that your disks are able to deliver to your CPU. Now think about whether or not your network is capable of that kind of throughput. In most cases, networks are measured in terms of gigabits, 1 gig, 10 gig, those kind of things. And so you can quickly realize that by doing a comparison like that a network is much slower than any internal or other I/O type of component within the data warehouse. And so minimizing as much as possible the data you need becomes critical, and then transferring it in an efficient way becomes absolutely paramount in terms of importance for your ETL. So minimizing transformations. So minimizing anything that might slow down that transfer of data over the network is absolutely important. So think very hard about your transformations, and I'll go through several scenarios in this video that will demonstrate that as well. Incremental loads. This is also very important. So if at all possible, it is best to do things in an incremental manner, extracting data in an incremental manner from the source. This is because incremental is by definition smaller, or a subset of the full load, and the full load just will take longer to move across your network. So that's what I had in terms of introduction. Now I want to get a little deeper into this topic. Now there's many ways to transfer data, and I'm going to concentrate on SQL Server and some of the more popular ways of transferring data to a SQL Server. And they can broadly fall into two categories that I've outlined for data warehouse scenarios. You have the OLTP kind of approach to ETL, and then the data warehouse. First, the OLTP. This is usually, on the right are some of the more popular ways of accomplishing data movement using an OLTP approach. This is using things like mirroring or availability groups in 2012, replication, and log shipping. The primary characteristic of this type of approach to ETL is that you are looking for transactional consistency. Again, this is the purpose of these, is to have some sort of backup or hot backup that you can always bring online if for some reason your production or your main system goes down. However, A database ETL is characterized not by transactional consistency in most cases, but by the state of the data. In other words, a snapshot or what the data looks like at a given point in time, usually by the end of the day. There is a technology in SQL Server called change data capture, which I've used many times. It is based on replication, however, and I will talk about it more in detail. However, it uses replication in such a way that it gives you the last row version for the queried time period. And so it does this data state approach as well, and is very good for an incremental type extraction scenario. I will also talk in great detail about integration services and how data is processed in integration services, and how choosing the right component is actually critical in having good performance from your integration services. Also, I put up here flat files, and flat files about 10 years ago when I started working with data warehouses was what I started working with. And I'll explain how flat files still can be, for many situations, the most efficient way to transfer data over the network, and I'll explain why that is in a little bit. So why do people choose an OLTP type approach to constructing their ETL? Well, for one, it's easy for most DBAs to set this up. It is technology that they're very familiar with. They're very familiar with replication or mirroring or even log shipping. And so this is something that they can set up with relative ease. This is usually characterized because of its nature of having the same data model as the source. And so if the source is in third normal form, which is almost always is, then of course your target or your data warehouse would be in third normal form as well. Again, I would characterize this not as a data warehouse, but as an operational data store. Again, the key here is transactional consistency. You have to replay all the transactions that occurred on the source system on the data warehouse or ODS server, in addition to having that same server supporting the reporting queries. While this does accomplish the goal of alleviating the source or OLTP operational system from having to support reporting queries, this puts a tremendous burden on the ODS server, especially if you're going to have multiple source servers that need to have all their transactions replayed on the data warehouse server. So, and that's where you run into scalability issues. Under this approach, it might work well for a handful of source systems to replay all their transactions on your data warehouse server and to have reporting queries running as well. But as you add more sources, this will become very difficult for your ODS or data warehouse server to perform well against, simply because many of these operations, such as updating, for example, produces an exclusive lock. You think about the isolation transactions and isolation levels. If you have an exclusive lock, your report queries they have to wait for that lock to be released, and if you are constantly having updates occurring from many source systems on your data warehouse server, this can quickly cause performance issues. Now, this type of approach isn't always bad. There is a very narrow scenario where this does work, but it needs to be, you need to think about this carefully. It can be used for what's called real-time data warehousing, or particularly if people want to see their data updated in their data warehouse on, let's say, an hourly basis, or 30 minutes every 30 minutes. Then these type of approaches can be used, but they must be used with great discretion and with careful attention to some of the issues I brought up previously. Typically, if this is a hard requirement, I like to separate this workload off into a separate set of disks and things like that to make sure it's fully segregated from the regular data warehouse pattern of scan type operations. So a data warehouse ETL is typified by daily loads, usually on a nightly basis, into your data warehouse server. Again, what we are concerned with here is the state of the data, not necessarily transactional consistency. There is no need to replay all the transactions on your data warehouse server. In fact, that is not desirable. Change data capture is a great way to pull data incrementally from a source if there's no other way to determine what the incremental changes are. It is fundamentally a transaction log reader and is related to replication technology. It converts your log sequence numbers, or your LSNs, into date time stamps. And then it tracks these changes in some separate metadata tables. These metadata tables will be in the CDC schema. And you can query these tables using a variety of stored procedures based on last ETL runtime to get the net effect of all your DML operations for any given row set. And so it is still accomplishing the same thing of giving the state of your data at even any given point based on your query. In other words, you can get net changes from your last runtime. This is equivalent to getting your row versions. So what I would like to transition to now is showing how you can process data with integration services. How integration services processes your data and the type of operations you want to perform on your data is of critical importance to making sure you have a scalable ETL solution. So in general, integration services has two ways of processing data, in a synchronous and an asynchronous manner. So first I will describe synchronous. And this is within the context of integration services, not within the context of a database engine. We'll get to the database engine a little bit later. So synchronous is a row-based. And logically, from a logical perspective, these type of transformations work on a row-by-row basis. Your memory buffers do not need to be changed. They are just simply reused. If you remember in integration services, you have buffers that run through your data flow tasks. And usually by default, these come in the form of a buffer of 10,000 rows. So for these synchronous transformations, no transformation of the buffers is required. Memory doesn't need to be copied and is simply processed logically on a row-by-row basis. Now this is what integration services does very well and very efficiently. And when I say row-by-row, I'm talking outside the context of a database engine and relational theory. This is for integration services only. The next major type of transformations are the asynchronous transformations. And some are partially blocking and some are fully blocking. So these type of transformations that are asynchronous require a certain amount of buffers to be spooled into memory. They don't continuously flow through the transform as in the synchronous. However, they need to be worked on. And the shape of the buffer will or might need to be changed. I'll get into specific examples of this in a few minutes. The fully blocking asynchronous components require all the buffers, or in other words, all the input rows from the source to be spooled into memory in that transform and then operated on. So, synchronous and asynchronous. Synchronous, the rows can flow through, their buffers can flow through as they arrive and are processed logically as they come. Asynchronous transformations, the rows are not processed as they come in, but all the rows need to be spooled into that transform and then operated on together. Okay? Those are the major ways you need to start thinking about processing data in integration services. So here are some practical examples of what the different components are and how or transforms are and how they fall into these categories. Under synchronous, you have things like conditional splits, lookup, and derived column. These are some of the more popular ones, and these are synchronous. And these can occur very quickly. These type of operations are very fast in integration services. For your asynchronous transformations, you have things like sort, aggregate, and merge join, or joining the data. These three are the more popular ones that I've seen in use, and can cause, if you're not careful, the most headache around performance of integration services. And it's because these are asynchronous. These are fully blocking operations. So now I will go through a demo of what it looks like when you process data with asynchronous or synchronous transformations as well. Here I have a very simple package that demonstrates the difference between asynchronous and synchronous transformations, and where you can visually see this occurring. In all 4 control flow components, I am querying the same table. The table is a 100 million row fact table that is data set expanded from EventureWorks that I have used in my previous videos. Please see I/O statistics in those videos to get a detailed understanding of this fact table and its characteristics. The top 3 control flow components are going to use data flows that are virtually identical. I'm going to select from my target, my source table, and in the million row transformation, I'm going to select the top million rows. Now these rows are going to be processed first synchronously using a derived column transformation. And I put in just an expression, a representative expression here for a new column. I'm just adding on a new column. And then the rows are going to be processed asynchronously using an aggregate transformation here. I'm going to aggregate by sales. I'm going to aggregate sales amount by sales territory key. That's why I have the group by on the sales territory key. And it's going to continue on. This multicast just resembles the rest of the package. Here you will be able to see side by side the difference in processing between the synchronous and asynchronous components. Now I've done this with 1 million rows, 2 million, and 4 million rows. The reason for this is because I want to show you what the performance is like. And I'm going to take note of the performance in terms of seconds for 1 million, 2 million rows, and 4 million rows. So what I'm going to do now is start the execution. Now this is started, and when the rows come in, you will see in the synchronous component that the rows continue on. However, here in the aggregation, they're all being spooled up and haven't reached the multicast yet until all 4 million rows reach the aggregate component. The reason for this is very simple. This is not a limitation on integration services, but by definition, if you want to aggregate all the rows, then you must have all the rows spooled into memory for the aggregate transformation to be able to operate on. And here comes my 7 rows as a result. Now that that is over, I can look 1 million, 2 million, and 4 million row processing. I can look at the progress and get the timing of these. So I'm going to collapse. Here's my 1 million, 2 million, and 4 million row aggregation processing. For my 1 million, that took about 2.7 seconds. to process to aggregate 2 million rows, in this example, took about 5.4 seconds. And finally, to process double that, 4 million rows, in my example, took about 10.8 seconds. So, I'm going to use approximations here. Looking at the results of these three aggregation operations on different sizes of data, you will see that there is a direct relationship, almost a linear relationship, between the number of rows being aggregated and the time it takes to perform that aggregation operation on those rows. In other words, the more rows that you need to aggregate in this manner with integration services, the longer that aggregation will take by definition. That is simply due to the fact that the aggregate component is a fully blocking asynchronous component that requires all the rows to be spooled in to memory in integration services and then to be operated on. So naturally, if you have more rows that you need to bring into memory, that need to be spooled into memory before they can be aggregated, then that will take longer to perform that operation. So there is a direct, almost linear relationship here. Now, in this fourth example, what I've used is this fact table that I'm using for my source has a column store index. And a column store index, you need to watch my previous videos, and particularly the column store index videos, is a way of optimizing the database engine for particularly what integration services refers to as asynchronous type operations. A database engine has many ways to optimize those type of operations, whereas integration services does not. And so here I'm again doing the exact same type of operation. I'm aggregating by sales territory key, and I'm summing the sales amount. And in this example, I've dropped all the buffers, so I'm pulling all this information directly from disk. And if I go to my progress again and look up how long that took, my 100 million rows, it took less than a second. In other words, to perform an aggregate operation in integration services on 1 million rows took almost 3 seconds. However, to perform the same aggregation using the database engine, particularly column store indexes, on 100 times the amount of data, took less than 1 second. And in fact, that time can be sped up. If I execute this once, and then execute it again, now that all the rows are stored in memory, I should get a faster time. And in fact, I do. I get 0.2 seconds. Or in other words, less than a half a second. Hopefully, this demonstration will help you understand the difference between processing data asynchronously with integration services as seen above in these three examples and the linear relationship that entails, and being able to use the database engine to perform these asynchronous type of operations. And the performance difference between those two can be substantial. So you need to think about the type of operations that you want to perform on your data for your ETL process and understand where it's most efficient to perform those operations, whether it be in integration services or on the database engine itself, using all the optimization techniques that I've described in previous videos. So, jumping back to my slides again, now with that in mind, I've pulled up a quick screenshot of an actual package that I've worked on recently. Now this wasn't a package designed by myself, but I use it as an example of using integration services to perform asynchronous transformations. Now I've purposely made this a little bit blurry, but you can still make out something, get some understanding of what's going on here. Here you have a source, you have a condition, you have a split or a multicast into some aggregations, some more sorting, some more joining, and additional aggregations and additional sorting going on. So you have lots of asynchronous type operations going on here. What this produces, and these are actual numbers from a customer, what this produces, as I've demonstrated before, is that asynchronous processing of data in integration services produces roughly linear performance. Now with the caveat that you have enough RAM to hold all these data. Remember, all these rows are going to be spooled into memory, and if they don't fit in memory, they're going to be spilled to disk, and that's going to increase your processing time almost exponentially. So assuming that you have enough RAM and enough CPU, you're going to get roughly a linear result in terms of how you scale these operations in integration services. Again, each fully blocking asynchronous component must spool all the rows into memory. The more rows you have, the longer your processing time is, and there is no way to process these rows faster. This is a very important part. As long as you have enough CPU and RAM, there's no way to kind of curve this line or to make it shallower, if you will, to decrease the inclination. That won't work. It doesn't matter what kind of server you put it on. Fundamentally, you have to spool all those records into integration services, and that single integration services transformation, like an aggregate transform, has to perform the aggregate operations on that. You don't have the benefit of any database engine optimizations, such as the query engine, statistics, compression, column store indexes. None of that's available in terms of processing those aggregations more efficiently. Integration services just simply does what the transform states. It aggregates the rows. This is a very procedural-like method of approaching an ETL, meaning and this is more popular with those who come from an application background, meaning you procedurally tell integration services how to process the data in an exact order, and it's the exact opposite of what a relational database engine is. It's relational. It uses relational theory and more a declarative approach, relational algebra and relational calculus to solve this problem for you in the most efficient way. Now this approach does have, in a limited fashion, a good application if you are in a VM or a SAN situation. That is because this approach minimizes the risk of I/O from disk to this server. You use that as little as possible in this type of approach. In other words, you're only transferring SQL Server is only a holding spot for this data. Once it's transferred out of SQL Server and integration services, it is then processed there until it's done being processed and you land it back into SQL Server. As long as your processing times are acceptable, following this linear graph here, then this approach can be used for those purposes. But remember, there is no tuning of this. It will not get any faster than how it exists. You might be able to process some of the data in different parallel chunks, but fundamentally you're not processing the data any faster. You're just dividing it into smaller chunks across many servers. One last note here is OLDB command is terrible for data warehouse type workloads because it is a component that for every record in your source data set, it executes a DML operation. The most popular scenario here is you have a source table and a target table. You want to update the target table based on source tables values for a given column, and so you feed in all the rows for the source table and you execute a distinct individual update statement for every row in your source data set. In other words, if you have 1 million rows in your source data set, then you will execute 1 million separate update commands based on that. That is the definition of row by row, and for data warehouse scenarios, that's a very inefficient way to process a lot of data. Use the database engine, particularly the T-SQL merge is a great option there. So that is all that I have for this particular video that really highlights integration services and the distinction between asynchronous and synchronous transformations. Next, I'll continue on with going into a little bit more detail around the ETL process and different methods for performing those type of operations as well. Thank you for your time.